Okay, our second speaker, Nathanael Arkor, talking about convolution via exponentiation. The floor is yours.
Thank you very much. And thank you to the organizers at Fest in general for inviting me to give a talk. The topic of my talk today is convolution in quite a general sense. And I think it'll be best if we just jump straight in and I'll remind you what convolution typically means in category theory. And then we'll see some examples that look very reminiscent but aren't quite fitting into the usual pattern. So let's start off with what convolution is. So if we're given a small monoidal category, here denoted C, then we can look at the category of presheaves on C. So this is the category of contravariant functors from C into the category of sets. And it's an old fact, which was originally established by Day, that the category of presheaves itself has a monoidal structure. And this is defined in terms of the monoidal structure on C itself. Now, the tensor product is defined using this formula, the details of which won't be important for this talk. The thing that will be useful is just to observe the general form of this formula because it's going to come up later. So given two presheaves, P and Q, the tensor product is defined by taking some colimit. So this is a coend here. So coend is a type of colimit. And we're multiplying P and Q at each object of the ambient monoidal category C, and then taking a product with the set of morphisms from X tensor Y into C, which is the object on which we're evaluating this tensor product presheaf. So it looks a little bit intimidating, perhaps. The unit is a bit simpler. It's just given by the representable presheaf on the unit object of the monoidal category. Now, this construction is very common in category theory. It's very useful for a number of reasons. But when you're first faced with it, it can seem a little complicated. So to actually prove that this does indeed define a monoidal structure takes a little bit of work. Usually it might be given as an exercise in getting to understand the coend calculus. But for one reason or another, this seems maybe a little awkward because given how fundamental this construction is, it would be nice to have a very simple proof that this does indeed define a monoidal structure. And in fact, there is a much simpler proof, which isn't very well known. So I want to mention it now. And the key to understanding how to simplify this definition is to observe that the tensor product in this presheaf category is defined using a colimit. And colimits have mapping out universal properties. And what this suggests is that we can probably gain something by trying to look at the situation multicategorically, because multi-categories are also defined in terms of mapping out in a suitable sense, which I'll mention in just a moment. So let's see what that looks like. Let me just remind you what a multi-category is. So multi-category is just like a category, but our morphisms can have multiple objects in a domain. That's really the only difference. In particular, if we have a monoidal category, we can view a monoidal category as a multi-category, and we're going to define a multimorphism from x1 through to xn to some object y as an ordinary morphism from the sort of iterated tensor product x1 tensor dot 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 tensor xn to y. And this defines a multi-category. And in fact, this describes an embedding of monoidal categories into multi-categories. And we call any multi-category arising in this way a representable multi-category. And in fact, this works for collapse monoidal categories too, where the associator and unitars are non-invertible. And we call such multi-categories weakly representable. How can we use this to understand convolution? Well, if we look at a natural transformation, so morphism in the presheaf category, from the tensor product into some other presheaf R, using the universal property of the coend and using the Linné dilemma, we can see that such natural transformations are in bijection with families of functions where we look at morphisms or functions from px times qy to r x tensor y. And these have to be natural in x and y. And similarly, if we look at natural transformations from the unit presheaf to some other presheaf, or just directly by the innate lemma, we see that these are in bijection with elements of R applied to the unit. And this suggests a general definition of a multimorphism in a presheaf category. So if we take our monoidal category C, then the presheaf category is equipped with the structure of a multicategory, where a multimorphism from P1 through to Pn to R is a family of functions P1 times X1, P2 times X2, P1 applied to X1 times P2 applied to X2, and so on, into R applied to X1 tensor X2 tensor, and so on till Xn. Now, it turns out that if you try to define this multi-category structure directly on the presheaf category, it's very easy. It doesn't take much work to show this does indeed define a multi-category, and it's a lot simpler than proving that the usual Cohen formula for the tensor product in the monoidal structure on a presheaf category is indeed a monoidal structure. And then once you've shown that you have a multi-category structure on C hat, it's fairly easy to show via some abstract nonsense that this does indeed form a monoidal category. So a tensor product exists essentially using an adjoint functor theorem. But this means that you can avoid a lot of the steps in constructing the monoidal structure directly. It sort of comes for free from the multi-category. So this is a very nice perspective on where the convolution monoidal structure comes from. Now, there's another advantage other than just being a simpler construction, which is that when we view things multicategorically, we see that the convolution monoidal structure has a universal property, which is very nice. So we can view C and set with the Cartesian product as representable multicategories. So viewing a monoidal category as a multi-category by looking at maps out of the tensor product. And then the multi-category structure on the presheaf category is precisely the exponential multi-category. So we look at the exponential of set, the multi-category set, to the multi-category C op in the category of multi-categories. So this is an observation of Claudio Pisani. And in fact, you can say even more than this. While not every multi-category is exponentiable, it's possible to characterize the multi-categories that are exponential, and they turn out to be precisely the promonoidal categories. Now, I'm not going to recap what a promonoidal category is, but if you're familiar with convolution, you've probably come across the statement that, in fact, you can define this tensor product on a presheaf category, not just for monoidal categories, but also promonoidal categories. That was the setting in which Day originally worked. And this gives a very nice conceptual explanation for why convolution works for promonoidal categories. Okay, so we have a sort of simpler description of the convolution structure, and we also have a nice universal property. But there's another advantage, which is particularly relevant for this talk, which is that by working with multi-categories rather than monoidal categories, it really simplifies studying structures internal to the monoidal category. So for instance, if we look at a monoid in a multi-category, this is just the same as the data of a functor from the terminal multi-category into that multi-category. And using the fact that the convolution monoidal structure is an exponential, we can see that a monoid in the convolution monoidal, or the convolution monoidal or convolution multi-category structure on the category of presheaves is a functor of multi-categories from 1 into the exponential. And then by transposing using the universal property, this is the same as a functor from COP to set. And functors of multi-categories between representable multi-categories correspond precisely to lax monoidal functors. So from this very simple derivation, we see that the monoids in the convolution monoidal structure on a presheaf category are precisely the lax monoidal functors from COP into set. You can also prove this using the Cohen calculus, but it's a bit more complicated than using the multi-categorical universal property. So this is very nice, and we'll be making use of this later in the talk. So that's a bit of background on the perspective I want to make use of for convolution for monoidal categories in this talk. And now we're going to move to a slightly more general setting. So it's often said that monoidal categories are just one object bicategories. And while this is true, it's often more helpful to think of monoidal categories as being examples of one object double categories. And the reason is, and don't worry for those of you who don't know what double category is, because I'll recap it in a moment. But the reason we might want to view a monoidal category, sorry, a double category is generalizing a monoidal category, is that we often want to view monoidal categories as being structure on top of a category. But bicategories are not structure on top of a category because bicategories don't have underlying categories, but double categories do. So if we want to view monoidal categories as structure on a category, then the most faithful generalization to a sort of multi-object notion of monoidal categories is a double category rather than a bicategory. So let me briefly record what a double category is, and then I'll say why we might be interested in looking at convolution for double categories. So double category is a structure a bit like a category, but we have two kinds of morphism. So one kind of morphism I'm going to draw vertically, and I'll call these tight morphisms. And the other class of morphisms I'll draw horizontally, and I'll call these loose morphisms. So along with these two kinds of morphism, we have data which fills squares like this, which I'll just call cells. And the idea is in a double category, we can compose in the loose direction or the tight direction. So I can compose these squares horizontally or vertically. The difference is when I compose vertically, this notion of composition is strictly associative and unital. So as associative and unital as composition in a category. Whereas if I compose in the loose direction, so horizontally, then this composition is only associative and unital up to some coherent isomorphism. So if you're familiar with bicategories, then it's very much analogous to this. I'm not going to spell out the details though. It suffices to know that we have these sorts of composition operations. The details are not going to be so important. Right, I wanted to mention one thing before giving you a couple of examples. So given any double category C, we can define two ordinary categories from it. So there's one more obvious category, which I'll call C naught, which is a category whose objects are the objects of the double category and whose morphisms are the tight morphisms, so the strictly associative and unital morphisms. But then we have another category, C1, whose objects are arbitrary loose morphisms in C, so you can have any domain and codomain. And the morphisms in C1 are the cells in C. So formally, I mean that the morphisms are triples comprising two tight morphisms at the side, so there's F and F prime at the bottom here, and also a cell phi filling the square. Again, the details of these two constructions are not going to be so important, but I will briefly mention them a little later. Now, let me give you a couple of examples. So there's a prototypical example of a double category whose objects are sets, whose type morphisms are functions, whose loose morphisms are spans of sets, and whose cells are morphisms of spans. So they're functions as on the right, so a function from P to Q, so between the apices of the spans, making the two squares commute. And you can define composition in the loose direction via pullback of sets. Now, another example is the double category of categories and distributors. So here, an object is a category, or a small category to be precise. A tight morphism is a functor. A loose morphism from y to x is a distributor. So it's a functor x op times y intercept. And the cells are simply natural transformations, as on the right. So you can think of this as sort of being a distributor as being a sort of categorified notion of relation, if you've not come across it before. But again, the specific examples are not going to be so important for what comes, but I just wanted to give you a flavor of what double categories can express. So here to compose distributors, we take some coends. So composition is via a colimit of a certain kind. Now, the principle I want to illustrate today is that it's often useful in category theory when we see some construction or some property of monoidal categories to try to generalize it to double categories. Now, there are many instances of this sort of phenomena being useful in the literature, which I'm not going to mention now. I'm just going to talk about the specific case of trying to generalize convolution from monoidal categories to double categories. And the reason we're going to be interested in this is that there turn out to be quite a lot of constructions in the literature that look quite like convolution, but they don't fit within the pattern I illustrated at the start of the talk. So they're not instances of convolution for monoidal categories or promonoidal categories. And we'd like to understand how they relate and whether there's a bigger picture they fit into, which would help relate these different strands of research. So the first example I want to give is sort of, sorry, I think there's someone's microphone isn't muted. Okay, so given
Claudio.
okay, I think it's muted now. Okay, so given sorry, a few slides ago, I said that one generalization of monoidal categories was bicategories. So bicategories can be viewed as sort of many object monoidal categories in some sense, or monoidal categories are one object bicategories. And so there's a similar construction of convolution for bicategories. So given a bicategory B, we can form a new bicategory B hat, which is called the local co-completion of B. And here, the hom categories of the bicategory are defined to be the presheave categories on the hom categories of the original bicategory. So we're taking the category of one cells and two cells between every pair of objects and taking presheaves on this category. And now we can define composition of one cell. So now the one cell is going to be presheaves. So to define their composition, we're going to use a convolution style formula. And again, the exact shape of this formula is not very important. What I really just want to show you is it looks very much like the convolution we saw before. So we're taking some coend, and here we're taking a coend over one cells in hom categories rather than objects of the monoidal category. And again, we're taking P of something times Q of something, and then taking the multiplication of this with the set of two cells from F composed G into H. So it looks very similar, but it's obviously not an instance of the previous construction because we're working with a bicategory rather than a monoidal category. Now let's see a second example. So there was a recent paper by Baer, Melies, and Zeilberger who defined a generalization of convolution from monoidal categories, where they showed that if instead of starting with a monoidal category, you start with a double category. So recall that I said for any double category C, there was an associated category C1, which was the category of loose morphisms and cells. So they showed that if you consider the category of presheaves on C1, this has not a monoidal structure, but a colax monoidal structure. So the associator and unitors are non-invertible. But again, the tensor product looks very similar to what we've seen before. So here, the tensor product of P and Q is a coend, and here we're taking a coend over objects of a certain category of composable pairs of loose morphisms, and we're taking a product of P with Q and with the set of cells from F composed G into H. So again, it has a very similar appearance to the previous convolution formulae, but it's not an instance of any of the previous ones. Now for the third example, I need to give a bit more context. So we're probably all familiar with the idea that if we want to study a category, it's often useful to embed the category in the category of presheaves using the innata embedding. And if we care about studying double categories, then it stands to reason that we might want to do something similar for double categories. You might want to study a double category C by embedding it into some double category of presheaves or something like this. But to do so, we need to answer the question of what is a presheaf on a double category in the first place, and then what structure do presheaves on a double category form? Now, you might think, well, the answer should be quite obvious. If we have a notion of presheaf on a double category, then presheaf should again form a double category. But actually, this isn't quite right, and this is what makes the situation rather interesting. So in 2011, Bob Parry studied this question and some related questions and showed that the appropriate notion of presheaf on a double category is a contravariant functor from C into the double category of spans. Now, a contravariant functor in this case means, well, we can take an opposite of a double category by flipping all the type morphisms around. And here, the appropriate notion of a functor of double categories is what's known as a lax functor. So it doesn't strictly preserve associativity and unitality of composition of loose morphisms. It only preserves them up to a non-invertible cell. Again, the details are not so important for now. Maybe the thing to note is that lax functors of double categories generalize lax monoidal functors. So Paré introduced this notion of presheaf on double categories, but he showed that they don't actually form a double category. They merely form what's known as a virtual double category, which I'm going to come to in just a bit. So while there is a well-defined Unedra embedding for double categories, it behaves a little differently from the Unedra embedding that we're used to for categories. And right now, the relationship to convolution might not seem very clear, but I'm going to come back to this shortly. So these three constructions are some of the constructions that motivated me to study this question of convolution in the context of double categories. Okay, so let's see how we can unify these three examples. So recall that at the beginning of the talk, I explained that if we want to understand convolution from monoidal categories, it's more helpful, it's simpler, and enlightening to move to the context of multi-categories. And so analogously, if we want to understand convolution for double categories, it stands to reason that we want to move to an analogously more general context. So if we are viewing monoidal categories as one object double categories, what structure recovers multi-categories when we restrict to the one object structures? Well, these turn out to be exactly the concept of a virtual double category. So let me tell you what those are, for those of you who have not come across them before. So a virtual double category is very much like a double category, except just as when we move from monoidal categories to multi-categories, we drop the assumption that we can take tensor products. In a virtual double category, we drop the assumption that we can take composites of loose morphisms. And to sort of fix the problem that now we can't talk about as much structure, in a multi-category, we introduce multimorphisms, and in a virtual double category, we introduce multi cells. So now we have cells that have multiple loose morphisms in their input. Now, just as in a double category, the typed morphisms compose strictly associatively and unitally, so they form a category. But because we can't compose horizontally anymore, so in the loose direction, our composition looks like composition of multi-category. So we can paste together the sort of rectangles with multi input. Here I've just sort of illustrated the structure of composition for binary multimorphisms or binary multi-cells. But in general, we can have any finite n for the number of loose morphisms in the domain. So again, the precise structure is not so important, but just this intuition that virtual double categories are a many object notion of multi-category will be the intuition that we need. Now, just as we can view monoidal categories as multi-categories, we can view double categories as virtual double categories. And here now the multi cells, so from P1 through to Pn into Q, are defined to be the ordinary cells in a double category from a composite P1 compose ... compose Pn into Q. And just as for monoidal categories, the functors between representable virtual double categories, so i.e. double categories viewed as virtual double categories, are the lax functors between double categories. So the appropriate notion of functor of double categories for this talk. Now, we come to the main theorem of the talk, and I'm going to give some examples. So the main theorem is that we have a similar story to the multi-categorical case. So just as every monoidal category, when viewed as a multi-category, was exponentiable, and the exponentiation captured convolution, so too does every representable virtual double category, i.e. an ordinary double category, so is every representable virtual double category an exponentiable virtual double category. And as we'll see on the next few slides, the exponentiation really does capture convolution in a very strong sense. So I won't go into the details of this. I just want to mention what the objects and loose morphisms are in the exponential virtual double category. So if we're given virtual double category C and D, then the underlying category, so sorry, let me say it like this. The objects of the exponential are functors from C0 to D0. So the underlying category of objects and type morphisms. They're not functors of virtual double categories, and that's important. So they're functors between underlying categories. The type morphisms are natural transformations, and the loose morphisms are morphisms of graphs. So we have a functor from this category C1, which is loose morphisms and unary cells, into D1. So this is some assignment sending every loose morphism in C to a loose morphism in D, and similarly for unary cells. Um, so the thing to note is it's maybe not what we expect. It's not, the objects are not functors of virtual double categories, and we'll come back to this point in just a moment. But let's see how this really does capture the examples we were interested in. So the first example was we start with a bicategory. Now every bicategory can be viewed as a double category where the only typed morphisms are identity morphisms. And so this means every bicategory can be viewed as an exponentiable virtual double category. Now we saw before there was an example of a double category, which is a double category of sets and spans. This is a virtual double category because every double category defines a virtual double category. And we can look at the exponential span raised to the power of B co. So co means we flip the direction of the two cells in B. Now, the objects of this virtual double category are going to be functors from the set of objects of B into the category of sets. But if we restrict this virtual double category to the representable presheaves, i.e. the objects of B, this exactly recovers the local co-completion of B. So if we restrict the representable presheaves, this is again a bicategory. So in fact, it has composition. And it turns out to be exactly the local co-completion. So this tells us that the local co-completion operation is indeed a notion of convolution in an appropriate sense when we move from monoidal categories to double categories. Now, for the second example, recall I said that virtual double categories sort of a many object generalization of monoidal categories. Well, then conversely, we can view every multi-category as a one object virtual double category, which I'll denote sigma m for the de-looping. So now if we take a double category C, we can look at the de-looping of the Cartesian monoidal category set viewed as a multi-category and raise the power of C op. Now, this turns out to again be a multi-category. So again, this exponential only has one object. So yeah, raising one object virtual double categories to powers preserves the property of having one object. So this is again a multi-category. And in fact, it turns out to be weakly representable. So it's induced by a collax monoidal structure. And just by sort of unwrapping the explicit description of this exponential, we see that the underlying category of this multi-category is exactly the category of presheaves on C1. And so this precisely recovers the collax monoidal structure that was defined as a notion of convolution for double categories by Baer, Méliès, and Zeilberger. Now, for the final example, we need one more definition. So recall that I mentioned one of the applications of multi-categories to convolution was we can view lax monoidal functors as monoids in this convolution monoidal structure in a very simple way. Now, the analog of a monoid, so a monoid is to a multi-category as a monad is to a virtual double category. So monad in a virtual double category comprises a loose morphism T and a binary cell expressing a multiplication and a nullary cell expressing the unit. And it happens that for every virtual double category X, we can define a new virtual double category, mont X, whose objects are the monads in X, whose type morphisms are monomorphisms, whose loose morphisms are monad bimodules, and whose cells are a notion of monad transformation. Now, in the description of the exponential before, I emphasized that the objects are only functors of categories, so not functors of double categories or virtual double categories. However, using this intuition, extending the intuition from monoid and convolution monoidal structure, suggests that to get the lax functors back, we ought to be considering monads. And indeed, this is exactly what happens. So for given double categories C and D, we can recover Pare's virtual double category of lax functors from C to D as the virtual double category of monads and bimodules in the exponential D to the C. I see I'm running out of time, so let me go to one last slide and then I'll wrap up. So the motivation for sort of caring about this description, I mean, okay, it might seem like a neat description that we can recover this construction of the virtual double category of lax functors through some a composite of two nice constructions, two simpler constructions. But in fact, it's even more useful than just simplifying the description, because both the exponential and the mods construction have a universal property. They're both right adjoints. And so this equips Pare's virtual double category of lax functors itself with a universal property, which allows us to derive a lot of nice properties, which I don't have time to go into. But you can see my slides afterwards if you're interested. And the one other application I wanted to mention is that this perspective gives a very nice proof of the relationship between fibrations for double categories and presheaves for double categories that simplifies and generalizes some existing proofs in the literature. But I'm going to wrap up now. So if you found any of this interesting, you can find essentially everything I talked about in this preprint, exponential virtual double categories and presheaves for double categories. The only thing that's missing is a link to local code completion, which will be in the next version I upload. So just to summarize, the takeaways I want you to have is that if you care about convolution, then try thinking about it multicategorically, because this simplifies things considerably. If you're interested in generalizing things from multicategories to or monoidal categories to double categories, the analog of multicategories is virtual double categories. And finally, these instances of convolution have appeared in the literature turn out to be special cases of exponentiation for virtual double categories, which turns out to be a very useful way to look at things. So I'll stop there. Thank you very much for attending.
Okay, thanks to speak. And is there any question? Feel free to unmute yourselves. Paolo?
Yeah, thank you. So if I understand correctly, in Pare's paper, which, by the way, I haven't read, that's part of the question, there is something like a perceived construction for double categories, which lands into span, right? And you mentioned that this is something like the right way to generalize the unit embedding to that context. In what sense is that the right way? Like what carries over? Why aren't we just looking at something into set or into rel? Like there must be something that works better using span, right? So what happens?
So for instance, yeah, one thing I didn't have time to mention is that just as every category has a Hom functor from C op times C into set, every double category has a Hom functor, which is a lax functor from C op times C into span. And it turns out that this embedding and the embedding into the virtual double category of lax functors that Pare considers satisfies a Yannay dilemma. And it satisfies the Yannay dilemma in two ways. Just as for categories, the Yannay dilemma talks about morphisms, like natural transformations. There are two Yannay dilemmas for double categories, one which talks about tight morphisms and one which talks about cells. And Parry shows that sort of there's all the sort of analogies you would expect for the theory, the Yannay theory for categories carries over to double categories in this way. So he gives various results which show that it works analogously to categories, and this is one justification.
I see. And does that give us the usual universal properties that we get for double categories? Like the usual unit dilemma gives us universal properties?
Right, yeah, you can express things like adjointness, for instance, using this unit lemma. Yeah, like you have a usual theory of representability for such presheaves, which captures adjointness and things like this. So yeah, so it really behaves in all the ways you'd hope for.
I see. Thank you. Thank you. That is really interesting. And will I find all this stuff in your paper or maybe in Bob Perez paper?
Yeah, yeah. Or I would say if you look at the introduction to my paper, it gives the background, it gives some context, and it explains the relationship between between the papers. So a little biased, but I would suggest that's a place to start, and you can go back and look at Bob's paper if you want more of the details from there.
Thank you. Thanks a lot.